Close your eyes and imagine floating in space. The view is breathtaking, Earth below, stars above, the profound silence of the void. Movies make spaceflight look elegant, even routine. Astronauts glide gracefully through stations, step onto alien worlds, explore the cosmos with apparent ease. But space is not forgiving. It's an environment fundamentally hostile to human life, filled with dangers that aren't always obvious. Some threats are well known: the vacuum, extreme temperatures, radiation. Others are subtle, insidious, easily overlooked until they become critical. Tonight, we'll explore what's really dangerous in space, not the dramatic explosions and asteroid impacts of science fiction, but the genuine, often surprising hazards that astronauts face. We'll discover how lunar dust, sharper than broken glass, can destroy equipment and harm lungs. How space debris, traveling at bullet speeds, threatens every spacecraft in orbit. How static electricity, a minor annoyance on Earth, becomes a serious threat in the dry vacuum of space. How inertia, simple momentum, makes every movement dangerous when there's no friction to slow you down. We'll examine radiation that silently damages DNA, micrometeoroids that strike without warning, the psychological strain of isolation, and the countless small hazards that make spaceflight one of humanity's most dangerous endeavors. This is the reality of space, beautiful, fascinating, and profoundly unforgiving. Space's most fundamental danger is the vacuum itself. Space isn't completely empty. There are a few atoms per cubic centimeter in low Earth orbit, fewer in deep space, but it's close enough to perfect vacuum that the difference doesn't matter for human survival. On Earth, we live at the bottom of an ocean of air. Atmospheric pressure at sea level is about 14.7 pounds per square inch. Nearly 1 ton of pressure on every square foot of your body. You don't notice because pressure inside your body equals pressure outside. But remove the outside pressure and things go wrong quickly. Contrary to popular belief, you don't instantly explode in vacuum. Your skin is strong enough to contain your body, but within seconds, severe problems begin. The air in your lungs expands. If you hold your breath, your lungs can rupture a fatal injury called pulmonary barotrauma. The correct response to sudden decompression is to exhale immediately, allowing air to escape safely. Water on your tongue, in your eyes, in your airways, begins to boil not from heat, but because at near zero pressure, water boils at body temperature. This is called ebullition. Your mouth and nose would feel like they're fizzing. Moisture in your airways boils and the vapor is exhaled, cooling you and freezing on whatever surface it touches. Within 10 to 15 seconds, oxygen-depleted blood reaches your brain. You lose consciousness, hypoxia from lack of oxygen. If rescued and repressurized within about 90 seconds, you'd likely survive with minimal lasting damage. Beyond 2 minutes, brain damage becomes likely. Beyond 3 or 4 minutes, death is almost certain. Only one person has experienced near vacuum and survived to describe it. In 1966, a technician testing a spacesuit in a vacuum chamber at NASA accidentally depressurized his suit. He remained conscious for about 14 seconds, later recalling that he could feel the water on his tongue beginning to boil before he passed out. The chamber was quickly repressurized and he recovered fully, suffering no permanent injury. The vacuum also causes rapid heat loss, not through conduction or convection. There's no air to carry heat away, but through radiation. Your body radiates infrared energy into space. In sunlight, you absorb more energy than you radiate, and you overheat, potentially reaching over 250 degrees Fahrenheit, 120 degrees Celsius, on the sun-facing side. In shadow, you radiate heat without absorbing sunlight, cooling rapidly, potentially dropping below negative 250 degrees Fahrenheit, negative 150 degrees Celsius on the shadow side. This temperature gradient is extreme. Spacesuits must insulate against both extremes simultaneously. One side of a spacecraft in sunlight can be hundreds of degrees hotter than the side in shadow. Without a suit's thermal control, an astronaut would experience both freezing and burning, depending on which side faced the sun. Spacecraft maintain internal pressure, of course. The International Space Station maintains about 14.7 pounds per square inches, equivalent to sea level on Earth. But maintaining this pressure requires robust hull design. A tiny hole from a micrometeoroid impact or stress fracture causes slow decompression. The ISS has experienced several small punctures patched with sealant or metal covers. A large breach could be catastrophic. The Russian Soyuz 11 mission in 1971 ended in tragedy when a valve accidentally opened during descent, depressurizing the capsule. The 3 cosmonauts were not wearing pressure suits. The capsule was too small for all 3 to wear suits. They lost consciousness within seconds and died within 1 minute. When the capsule landed automatically, recovery crews found all 3 dead, the only humans to die in space itself, rather than during launch or re-entry. Modern spacecraft have better safety measures. Astronauts wear pressure suits during launch and re-entry. Hull punctures are detected by pressure sensors. Compartments can be sealed off. Airlocks prevent the entire station from depressurizing when astronauts go outside. Still, the vacuum remains space's most immediate threat: instant, unforgiving, and always just beyond the hull. Moon dust seems innocuous, fine grey powder covering the lunar surface. But it's one of the most insidious hazards astronauts have encountered, capable of destroying equipment, damaging suits, and potentially harming human health. Lunar dust, or regolith, forms from billions of years of meteorite impacts, grinding surface rock into powder. Unlike Earth sand, smoothed by wind and water into rounded grains, lunar dust particles are sharp, jagged, and angular. Under a microscope, they look like shards of broken glass with razor-sharp edges and points. This sharpness is a serious problem. Lunar dust is abrasive in the extreme. During the Apollo missions, astronauts found that just a few hours of walking on the moon abraded the soles of their boots significantly. Dust worked its way into the joints of spacesuits, scratching seals and making them harder to move. In some cases, suit joints became so contaminated with dust that they seized up. The dust sticks to everything. On the airless moon, with no moisture or atmosphere, static electricity causes dust to cling to surfaces. Astronauts returning from moonwalks were covered in dust on their suits, gloves, boots. The dust resisted brushing off. Once inside the lunar module, it contaminated everything it touched. The smell was distinctive and surprising. Astronauts described lunar dust as smelling like gunpowder or spent ammunition, a sharp, acrid odor. This smell came from chemical reactions when the dust, which had been exposed to the solar wind in vacuum, encountered the oxygen and moisture of the lunar module's atmosphere. But smell was the least concern. Inhaling lunar dust posed potential health risks. After moonwalks, as astronauts removed their helmets in the lunar module, some inhaled small amounts of dust that had contaminated the cabin. They experienced symptoms resembling hay fever, congested sinuses, sore throats, watery eyes. Apollo 17 astronaut Harrison Schmitt, a geologist, reported particularly severe reactions, calling it lunar dust hay fever. The long-term effects of inhaling lunar dust are unknown. No Apollo astronaut spent more than 3 days on the moon, limiting exposure. But studies of lunar samples show the dust is highly abrasive and could potentially damage lung tissue if inhaled in quantity. The sharp particles could embed in lung tissue, causing inflammation or scarring similar to silicosis, a lung disease caused by inhaling silica dust. Lunar dust also conducts electricity weakly, potentially causing short circuits in electronics. It's charged by solar radiation, causing it to levitate slightly above the surface and travel in clouds. Cameras, scientific instruments, and suit joints all suffered from dust contamination during Apollo missions. For future long-duration lunar missions, lunar bases, mining operations, dust will be a major engineering challenge. Airlocks will need sophisticated dust removal systems. Spacesuits may require hard lower bodies, like diving suits, rather than flexible fabric, to resist abrasion. Equipment will need sealed designs, preventing dust intrusion. Some proposed solutions include electrostatic dust shields using electric fields to repel charged dust particles. Others suggest coating surfaces with materials that don't accumulate static charge. Habitats might be built underground, away from surface dust. Roadways might be paved with sintered regolith lunar dust, melted and fused into solid pavement using solar concentrators or microwave energy. Mars presents similar dust challenges. Martian dust is finer than lunar dust. Particles are smaller, carried by wind across the planet's surface. The famous Martian dust storms can engulf the entire planet, lasting for months. While less sharp than lunar dust, wind has smoothed the grains somewhat. Martian dust is still abrasive and electrostatically charged. The Mars rovers' Spirit, Opportunity, Curiosity, Perseverance all struggle with dust accumulation. Dust settles on solar panels, reducing power generation. The Opportunity rover's mission ended when a global dust storm in 2018 blocked sunlight, draining its batteries. Dust infiltrates rover mechanisms despite careful sealing. For human Mars missions, dust will be an even greater challenge. Astronauts will track it into habitats. It will contaminate life support systems. If Martian dust has health effects similar to lunar dust, causing respiratory irritation, or worse, astronauts could face serious problems during long surface missions. Research continues on lunar and Martian dust hazards. Understanding and mitigating dust is essential for long-term human presence on other worlds. This grey powder, so innocuous in appearance, is one of space exploration's most persistent and insidious dangers. Earth orbit is increasingly crowded. Decades of space activity have left behind a growing cloud of debris, defunct satellites, spent rocket stages, fragments from collisions and explosions. This debris, traveling at orbital velocities of several miles per second, poses a significant threat to operational spacecraft and astronauts. As of 2024, tracking systems monitor over 34,000 objects larger than 10 centimeters in low Earth orbit. These are the pieces we can track. There are an estimated 900,000 objects between 1 and 10 centimeters, and over 130 million pieces smaller than 1 centimeter. Most are too small to track, but large enough to damage or destroy a spacecraft. At orbital velocities about 17,500 miles per hour in low Earth orbit, even tiny debris carries enormous kinetic energy. A 1 centimeter aluminum sphere at orbital velocity has the kinetic energy of a bowling ball dropped from a 5-story building. A 10-centimeter object has the energy of several sticks of dynamite. Collisions at these speeds are devastating. In 2009, an operational U.S. Iridium communications satellite collided with a defunct Russian Cosmos satellite over Siberia. Both satellites were traveling at about 26,000 miles per hour relative to each other. The collision completely destroyed both satellites, creating over 2,300 tracked fragments and thousands more too small to track. This was the first collision between two intact satellites, an event that had been predicted but hoped would never occur. The collision dramatically increased the debris population in the affected orbital altitude about 500 miles. These fragments remain in orbit, posing collision risks to other satellites. Some will eventually re-enter the atmosphere and burn up a process that takes years or decades depending on altitude. But many will remain in orbit for centuries. Deliberate destruction of satellites, anti-satellite weapons tests, creates even more debris. In 2007, China tested an anti-satellite missile by destroying one of its own weather satellites at about 530 miles altitude. The test created over 3,000 tracked fragments, which spread into a debris cloud, endangering satellites at similar altitudes. In 2021, Russia conducted a similar test, destroying one of its old satellites and creating over 1,500 tracked fragments. These tests are widely condemned because they create long-lasting hazards in heavily used orbits. The International Space Station operates at about 250 miles altitude in a region with significant debris concentration. NASA tracks all known debris and calculates collision probabilities. If the probability of a dangerous conjunction exceeds 1 in 10,000, the ISS performs a debris avoidance maneuver using thrusters to slightly adjust its orbit, ensuring the debris passes safely. The ISS performs several debris avoidance maneuvers per year. In 2020, the station performed 3 such maneuvers. In some cases, debris is detected too late for a maneuver, forcing the crew to shelter in their Soyuz or Crew Dragon spacecraft, ready to evacuate if the station is damaged. The ISS is armored against small debris. Whipple shields layers of thin material separated by gaps protect critical modules. When a small debris particle strikes the outer layer, it vaporizes and fragments. The inner layers catch the fragments before they penetrate the hull. This system protects against debris up to about 1 centimeter. Larger debris would penetrate, potentially causing catastrophic decompression. Satellites and spacecraft face similar risks. Many satellites in crowded orbits have been damaged by debris impacts. Most strikes involve particles too small to track paint flecks, metal fragments, solid rocket propellant residue. A tiny paint fleck traveling at orbital velocity can pit spacecraft windows or damage solar panels. The Space Shuttle's windows frequently sustain damage from debris and micrometeoroid impacts. After each flight, windows had to be inspected and often replaced. On one mission, a paint fleck about 0.2 millimeters in diameter created a pit about 2 millimeters across in a window, a 10-fold magnification of the impactor's size, demonstrating the extreme energy of orbital impacts. The Kessler syndrome, proposed by NASA scientist Donald Kessler in 1978, describes a potential runaway process. As debris accumulates, collisions become more likely. Each collision creates more fragments, increasing collision rates further. At some point, collisions cascade, exponentially increasing debris until certain orbital altitudes become unusable, too dangerous for satellites or spacecraft. Some orbital altitudes may already be approaching this critical density. Mitigating debris is challenging. Regulations now require satellites to deorbit within 25 years of end of life, either by controlled descent into the atmosphere or by moving to a graveyard orbit away from operational satellites. New satellite designs minimize debris creation, fewer explosive bolts, better battery designs that don't explode, and passivation, venting fuel and batteries, at end of life to prevent explosions. Active debris removal, capturing and deorbiting defunct satellites and debris is being developed. The European Space Agency's ClearSpace 1 mission, planned for the late 2020s, will demonstrate capturing and deorbiting a defunct satellite. Japan's ELSA-D mission tested rendezvous and capture technologies in 2021. These are first steps toward cleaning up orbit, but the debris problem will worsen before it improves. Mega constellations, thousands of satellites in coordinated networks like SpaceX's Starlink, are dramatically increasing the number of objects in orbit. While these satellites are designed to deorbit at end of life, the sheer number increases collision risk. If even a small percentage fail and become debris, they could substantially increase hazard levels. Space debris is a tragedy of the commons. All spacefaring nations contribute to the problem. All suffer the consequences. Only through international cooperation and responsible practices can we preserve Earth orbit for future use. Otherwise, our own space junk may eventually imprison us on our planet, making low Earth orbit too dangerous to traverse. On Earth, static electricity is a minor nuisance, a shock when you touch a doorknob after walking on carpet, clothes clinging from the dryer. In space, it's a serious hazard that can damage equipment, endanger spacewalks, and even threaten lives. Space is an ideal environment for static electricity. The near-perfect vacuum contains no moisture to dissipate charge. Materials become excellent insulators. Friction from moving parts or rubbing materials generates charge easily. And without moisture or atmosphere to conduct it away, charge accumulates to dangerous levels. During the Apollo missions, astronauts experienced severe static electricity problems. Lunar dust, as discussed earlier, is highly charged from solar wind exposure. When astronauts walked on the moon, their boots and suits accumulated electric charge. Returning to the lunar module, they sparked when touching metal surfaces, sometimes seeing visible arcs. This was concerning because the lunar module's atmosphere was pure oxygen at low pressure, a highly flammable environment. A spark could potentially ignite something, causing a fire. The Apollo 1 tragedy in 1967, which killed 3 astronauts during a ground test, resulted from a fire in a pure oxygen atmosphere. Any ignition source, including static discharge, was a serious threat. Astronauts took precautions. They grounded themselves before touching equipment. Lunar suits had conductive pathways to bleed off charge, but the dust was so invasive and charged that complete protection was difficult. On several missions, astronauts reported concerning static discharges. On the International Space Station, static electricity remains a concern. The station's dry atmosphere relative humidity is kept low to prevent mold and corrosion, promotes static charge accumulation. Astronauts sometimes receive shocks when touching equipment. While painful, these shocks are usually harmless. But near sensitive electronics, a discharge could cause damage. Spacewalks present particular static hazards. Spacesuits accumulate charge as astronauts move and as their suits rub against structure. Suits are designed with conductive pathways to ground this charge through the tether connecting them to the station. But if insulated from ground, an astronaut could accumulate significant charge. A fully charged astronaut touching a conductive spacecraft part could create a spark. In the suit's oxygen-rich environment, this could ignite materials. While modern spacesuits don't use pure oxygen, they use a mixture with nitrogen. Fire risk remains. Additionally, the discharge could damage the astronaut's communication or life support systems, both of which rely on sensitive electronics. Satellites face static hazards from Earth's radiation belts. Charged particles, electrons and protons trapped in Earth's magnetic field strike satellite surfaces, depositing charge. Over time, this charge accumulates. If it builds sufficiently, it discharges suddenly through the satellite systems, potentially damaging electronics. This phenomenon, called spacecraft charging, has damaged or destroyed several satellites. In 1998, the Galaxy 4 satellite failed when accumulated charge discharged through its control electronics, disabling the spacecraft and cutting off pager service to millions of users in the United States. Similar failures have occurred in other satellites, particularly those in geostationary orbit where radiation levels are high. Engineers designed satellites with conductive coatings and grounding systems to bleed off charge before it accumulates to dangerous levels. Solar panels are particularly vulnerable. Each cell must be carefully grounded. But perfect protection is difficult, and spacecraft charging remains a significant hazard. The solar wind-charged particles streaming from the sun also causes charging. During solar storms, particle flux increases dramatically, accelerating charge accumulation. Satellites in interplanetary space must be designed to handle charging from solar wind exposure. Static discharges can also interfere with scientific instruments. Particle detectors measuring cosmic rays or solar wind particles can be fooled by discharge events that mimic particle impacts. Careful design and shielding are required to distinguish real particle detections from static discharges. In microgravity, static electricity can cause strange effects. Small objects floating in the station, dust particles, droplets of water, loose screws can become charged and attracted to or repelled from surfaces. Charged objects might float toward an astronaut's face or stick to equipment. While not dangerous, it's annoying and potentially problematic if a charged metal screw floats into electronics. Future missions to asteroids or other airless bodies will face static challenges similar to those on the Moon. Landing on an asteroid, sampling its surface, or mining it will all involve handling regolith that may be highly charged from solar wind exposure. Robotic spacecraft touching asteroids have experienced unexpected forces, possibly from electric charge interactions, complicating sample collection. Dust devils on Mars, whirlwinds of dust, generate substantial static charge. Measurements from Mars rovers show electric fields during dust devils reaching thousands of volts per meter. Human explorers on Mars could potentially be struck by electric discharges during dust storms. Suits and equipment will need protection against this hazard. Mitigating static electricity in space requires careful material selection, conductive coatings, grounding systems, and operational procedures. Astronauts are trained to ground themselves before handling sensitive equipment. Habitats maintain some humidity to help dissipate charge. Conductive pathways ensure charge can't accumulate dangerously. Despite precautions, static electricity remains an ongoing concern. It's a subtle hazard, not as dramatic as vacuum exposure or radiation, but capable of causing significant damage or endangering missions. In space's dry, insulating environment, what's a minor annoyance on Earth becomes a genuine threat. On Earth, friction is everywhere. Move something and it slows down. Drop something and it falls. Throw something and air resistance eventually stops it. This constant friction shapes our intuitions about motion. Objects naturally come to rest unless something keeps them moving. In space, these intuitions are dangerously wrong. Without air resistance or surface friction, Newton's first law, an object in motion stays in motion, applies perfectly. This makes simple movements hazardous and routine tasks complex. An astronaut floating in the ISS who pushes off a wall begins moving and doesn't stop until hitting something. If they push off hard, not aimed correctly, they might tumble uncontrollably. Without friction, there's no automatic way to stop rotating or moving. They must push against something else, carefully applying force in the opposite direction to arrest their motion. This makes navigation inside the station tricky. Experienced astronauts move gracefully, using light touches on handrails to direct themselves. New astronauts often push too hard or in the wrong direction, careening across modules and bouncing off walls. Learning to move efficiently in microgravity takes time and practice. Inertia affects everything. A large, massive object floating weightless seems easy to move, just push it. But mass doesn't disappear in microgravity. A massive object has enormous inertia. Push it and it starts moving, but stopping it requires equal and opposite force. If it's moving toward you, you must exert substantial force to stop it or get out of the way. During the Skylab missions in the 1970s, astronauts manually moved a solar panel weighing several hundred pounds. In microgravity, they could easily start it moving. It floated weightless, but its inertia was unchanged. Once moving, it took considerable effort to stop. If an astronaut got between the panel and a wall while it was moving, they could be crushed. The panel's momentum would overcome their ability to push back. Tools and equipment present similar hazards. A wrench floating across a module seems harmless. It's weightless, moving slowly. But if it's massive and moving, catching it means absorbing its momentum. A fast-moving wrench can hurt, transferring its momentum into your hand with considerable force. Astronauts learn to intercept floating objects gently, matching velocity rather than trying to stop them abruptly. Rotation is particularly problematic. An astronaut who starts spinning has no easy way to stop. On Earth, you can stick out a foot and drag it on the ground. In space, there's nothing to push against. The astronaut must grab a fixed object or wait until drifting close to a wall to push against it. Uncontrolled tumbling is disorienting and potentially dangerous. An astronaut could strike equipment or injure themselves. During spacewalks, inertia becomes even more critical. Spacesuits are bulky and massive, with significant inertia. Moving and positioning the suit requires constant attention. If an astronaut starts rotating, stopping the rotation is difficult. Jetpacks on some spacesuits allow controlled movement, but must be used carefully. A thruster fired too long can send an astronaut tumbling or drifting away. Tethers are essential during spacewalks, keeping astronauts physically connected to the spacecraft. But tethers complicate movement. Pulling on the tether starts the astronaut moving toward the attachment point, but also pulls the attachment point toward the astronaut. If the attachment isn't secure, it can come loose, and tethers can become tangled, especially if an astronaut is rotating. In 1984, astronaut Bruce McCandless made the first untethered spacewalk using the Manned Maneuvering Unit, a jetpack allowing free flight away from the shuttle. This demonstrated controlled movement in space using thrusters, but it was risky. If the jetpack failed, McCandless had no way back. Subsequent untethered spacewalks have been rare, used only when absolutely necessary. Inside spacecraft, conserving angular momentum causes strange effects. An astronaut floating freely, who extends their arms and rotates, will spin faster when they pull their arms in, like a figure skater spinning. This makes intentional rotation useful. Astronauts can control spin rate by extending or retracting limbs. But it also means accidental rotations can accelerate unexpectedly. Moving large objects requires teamwork and planning. When the ISS receives a new module or large piece of equipment, astronauts must maneuver it into position. This involves careful, coordinated pushing and pulling, with multiple astronauts working together to control the object's motion. Even with several people, a massive object's inertia makes it challenging to position precisely. Docking spacecraft face inertia challenges. Two spacecraft approaching each other each have substantial momentum. If they collide too hard, the impact can damage docking mechanisms or even puncture hulls. Docking must occur. Gently approaches are slow and carefully controlled. But even at low speeds, the combined mass means considerable force at impact. Docking mechanisms include springs and dampers to absorb this force gradually. In 2021, Russia's Nauka module docked to the ISS. Shortly after, its thrusters unexpectedly fired at full thrust, pushing the entire station. The ISS began rotating, an alarming situation. Controllers used thrusters on other modules to counteract the rotation and stabilize the station. The incident demonstrated how thrust and momentum can affect even a large structure like the ISS. For future missions involving rendezvous and docking, servicing satellites, assembling large structures in orbit, retrieving samples from other spacecraft, managing inertia and momentum will be critical. Automated systems must be precise. Astronauts manually guiding spacecraft must have excellent training and situational awareness. Inertia affects psychology too. On Earth, we're used to objects behaving in certain ways. In microgravity, those expectations are wrong. This cognitive dissonance can cause mistakes. An astronaut might push off, assuming they'll slow down, then crash into equipment when they don't. Training helps, but the adjustment is significant. The lesson of inertia in space is simple but profound. Mass and momentum don't disappear just because weight does. Microgravity makes movement seem effortless, but physics remains. Astronauts must constantly remember Newton's laws and plan every movement carefully. Inertia, the tendency of objects to keep doing what they're doing, is a subtle but ever-present danger in space. Space is flooded with radiation, high-energy particles, and electromagnetic waves from the sun, distant stars, and cosmic sources. On Earth, we're protected by the atmosphere and magnetic field. In space, this protection is absent, and radiation becomes one of the most serious long-term threats to human health. There are several types of space radiation. Solar radiation particles and light from the sun is continuous but varies with solar activity. Galactic cosmic rays, high-energy particles from outside the solar system are constant. Radiation trapped in Earth's magnetic field, the Van Allen belts, poses hazards to spacecraft passing through. And solar flares, sudden bursts of intense radiation, can deliver dangerous doses over hours or days. Solar radiation includes ultraviolet light, blocked by spacecraft and suit materials, X-rays, partially blocked, and solar wind-charged particles streaming from the sun at hundreds of miles per second. Solar wind is mostly protons and electrons. At Earth's distance, solar wind delivers a continuous low-dose radiation exposure that accumulates over time. Galactic cosmic rays, GCRs, are high-energy particles, primarily protons, but also heavier atomic nuclei, accelerated to near light speed by distant supernovae and other cosmic events. GCRs have enormous energy, enough to penetrate spacecraft walls, spacesuits, and human tissue. They're impossible to shield against completely with current technology. When GCRs strike matter, they create cascades of secondary particles, neutrons, gamma rays, fragments of atomic nuclei. These secondary particles can be more damaging than the original cosmic ray. This means thick shielding can sometimes make radiation worse rather than better, a phenomenon called secondary radiation. Radiation damages biological tissue by ionizing atoms, stripping electrons from molecules. In human cells, ionization can break chemical bonds in DNA, causing mutations. Some mutations are harmless. Others can kill cells. Some cause cancer mutations that make cells grow uncontrollably, and some mutations affect reproductive cells, potentially causing genetic damage passed to future generations. Acute radiation exposure, a large dose over a short time, causes radiation sickness. Symptoms include nausea, vomiting, fatigue, and at high doses, immune system failure, internal bleeding, and death. The lethal dose killing 50% of exposed individuals is about 4 to 5 sieverts delivered over a short period. Astronauts in space are not at risk of acute radiation exposure. Under normal circumstances, doses accumulate slowly over months or years. But chronic exposure, low doses over extended periods, increases cancer risk. NASA limits astronaut career radiation exposure to keep lifetime cancer risk increase below 3%. For a 30-year-old male astronaut, this limit is about 0.6 sieverts, 600 millisieverts, over their entire career. For a 30-year-old female, it's lower, about 0.4 sieverts, because women have higher cancer risk from the same radiation dose. On the ISS, astronauts receive about 150 to 200 millisieverts per year, about 50 times the annual dose for people on Earth. A 6-month ISS mission delivers about 75 to 100 millisieverts, equivalent to several thousand chest X-rays. This is within career limits for most astronauts, allowing multiple ISS missions. But beyond Earth's magnetic field, radiation levels are much higher. The Moon receives about 300 to 600 millisieverts per year. Mars receives about 200 to 300 millisieverts per year. A trip to Mars, about 9 months each way, plus time on Mars, would expose astronauts to 600 to 1000 millisieverts or more, consuming a large fraction of their career limit in a single mission. Solar flares present acute dangers. During a major solar flare, radiation flux increases by factors of hundreds or thousands. The most intense flares deliver doses of tens or even hundreds of millisieverts per hour. Astronauts caught outside during a major flare could receive dangerous doses within hours. In 1972, between Apollo 16 and 17, a massive solar flare occurred. If astronauts had been on the Moon, they would have received potentially lethal doses. The Apollo program was fortunate that no flares occurred during moonwalks. Future lunar missions will need better solar weather forecasting and radiation shelters where astronauts can retreat during flares. Mars missions will require radiation shielding. Spacecraft walls provide some protection. Aluminum several centimeters thick reduces radiation by about 10–20%. Water is an even better shield. It absorbs radiation without creating as much secondary radiation. Some Mars mission designs use water tanks surrounding crew quarters as radiation shields. On Mars, astronauts can shelter underground or cover habitats with Martian soil, providing substantial shielding. Lava tubes, underground tunnels formed by ancient lava flows, could shelter bases from radiation. But during the long transit to and from Mars, astronauts will accumulate significant doses with no easy way to shield completely. Radiation affects more than just astronauts. Electronics are damaged by radiation, particularly by heavy ions that can cause single event upsets, where a single particle flips a bit in computer memory, causing errors. Spacecraft designers use radiation-hardened electronics components designed to tolerate radiation. But hardening increases cost and weight, and even hardened electronics can fail under intense radiation. Solar panels degrade from radiation exposure. Over years in space, solar cells become less efficient as radiation damages their structure. Satellites in high radiation orbits like geostationary orbit require more robust solar panels to compensate for degradation. Cameras are affected by radiation. Images from space often show bright spots or streaks, cosmic rays striking the camera sensor. Video from the ISS occasionally flashes as cosmic rays hit the camera. Astronauts sometimes see flashes of light when cosmic rays pass through their eyes, literally seeing individual particles. Mitigating radiation is challenging. Physical shielding helps, but has limits. Active shielding using magnetic fields to deflect charged particles has been proposed but requires enormous magnetic fields and power, making it impractical with current technology. The best current approach is minimizing exposure time, getting to destinations quickly, and using available shielding. Astronauts are monitored for radiation exposure using dosimeters devices that measure accumulated dose. If an astronaut approaches career limits, they may be grounded from future missions. Some astronauts have ended careers early due to radiation exposure, unable to fly again without exceeding safety limits. The long-term health effects of space radiation are uncertain. We have limited data. Only a few hundred humans have been to space, and most for short periods. Studies of atomic bomb survivors, radiation therapy patients, and nuclear workers provide some information, but space radiation has different characteristics: more heavy ions, continuous exposure, combined with microgravity. NASA and other space agencies are studying radiation effects extensively. Animal experiments on the ISS examine how radiation and microgravity together affect biology. These studies will guide countermeasures for future long-duration missions. Radiation is perhaps space's most insidious threat. Unlike vacuum or debris, it's invisible and silent. You can't feel it, see it, or know you're being exposed until damage is already done. It's the price of leaving Earth's protective cocoon, a risk we must accept and manage as we venture deeper into space. Space isn't empty. It's filled with small particles, dust from comets, fragments from asteroids, debris from past collisions. Most are tiny, smaller than a grain of sand. But at the speeds they travel, even these microscopic particles pack tremendous energy. These particles are called micrometeoroids, natural debris, as opposed to human-made space debris. They're everywhere in the solar system, more concentrated in some regions than others. Near Earth, micrometeoroid density is relatively low but not negligible. Farther out in the asteroid belt or near Jupiter, densities are higher. Micrometeoroids travel at speeds typically between 10 and 70 kilometers per second, 22,000 to 156,000 miles per hour. At these velocities, even a particle the size of a grain of sand carries kinetic energy comparable to a bullet. A millimeter-sized particle at 20 kilometers per second has energy equivalent to a .22 caliber bullet. And unlike bullets, micrometeoroids can strike from any direction without warning. Spacecraft hulls are designed to withstand micrometeoroid impacts up to a certain size. The ISS uses Whipple shields, 2 layers of material separated by a gap. When a micrometeoroid strikes the outer layer, it vaporizes and fragments. The inner layer catches the fragments before they penetrate the hull. This system protects against particles up to about 1 centimeter. Larger particles are rare but exist. A 10-centimeter object striking a spacecraft would be catastrophic. penetrating any realistic shielding and causing explosive decompression. Fortunately, objects this large are rare enough that the probability of impact during a typical mission is low but not zero. The Space Shuttle experienced numerous micrometeoroid impacts. After each mission, engineers inspected the shuttle for damage. Windows often had pits and cracks from small impacts. Thermal tiles, the heat shield protecting the shuttle during re-entry, frequently showed impact damage. Most damage was minor, but the cumulative effect over many missions was significant. The thermal protection system on the shuttle's leading edges was particularly vulnerable. These reinforced carbon-carbon panels withstood extreme heat during re-entry, but were relatively fragile. A large micrometeoroid or debris impact could crack or penetrate them, potentially causing a catastrophic failure during re-entry. The Columbia disaster in 2003, while caused by launch debris rather than micrometeoroid impact, demonstrated the consequences of hull damage. A piece of foam from the external fuel tank struck the leading edge of Columbia's wing during launch, creating a hole. During re-entry, hot gases entered through the hole, destroying the wing and causing the shuttle to break apart. A large micrometeoroid impact could cause similar damage. Satellites face constant micrometeoroid bombardment. Solar panels are especially vulnerable. Large, thin surfaces exposed directly to space. Small impacts pit and damage solar cells, gradually reducing power generation. Over years, the cumulative damage can significantly degrade a satellite's power output. The James Webb Space Telescope, positioned at the L2 Lagrange point about 1,000,000 miles from Earth, experiences regular micrometeoroid impacts. Its large mirror, 6.5 meters across, is exposed directly to space. Between May 2022 and its first year of operation, at least one micrometeoroid impact was significant enough to slightly degrade the telescope's performance, causing a small but measurable distortion in one mirror segment. Engineers expected micrometeoroid impacts and designed Webb's mirrors to tolerate them. The telescope can adjust mirror segments to compensate for damage. But the impact was larger than expected, occurring earlier in the mission than statistical models predicted. This highlighted that our understanding of micrometeoroid populations is incomplete. There may be more large particles than we thought. Meteor showers, annual events when Earth passes through comet debris trails, increase micrometeoroid risk. During major showers like the Perseids, August, or Leonids, November, flux increases substantially. Spacecraft operators take precautions orienting satellites to minimize exposed area, postponing spacewalks, or even sheltering ISS crew if the risk is particularly high. The 1,999 Leonid meteor shower was particularly intense. Predictions suggested elevated impact risk, and many satellite operators took protective measures. Some satellites reported anomalies likely from micrometeoroid impacts during the shower. Fortunately, no spacecraft were lost, but the event demonstrated the real risks meteor showers pose. Astronauts during spacewalks are personally at risk from micrometeoroid impacts. Spacesuits have multiple layers, the outer layer designed to protect against small particle impacts. But a sufficiently large or fast particle could penetrate the suit, causing rapid decompression. The probability is low during a single spacewalk, but over many spacewalks across many missions, the cumulative risk is non-trivial. NASA tracks known micrometeoroid streams and schedules spacewalks to avoid high-risk periods when possible. During spacewalks, astronauts are monitored, and if suit pressure drops unexpectedly, they're brought inside immediately. Suit designs include self-sealing layers that can close small punctures, though this wouldn't help against large impacts. Looking forward, missions to asteroids or comets will encounter much higher micrometeoroid densities. The asteroid belt, despite its name, is mostly empty, but still has particle densities higher than near Earth. Spacecraft visiting asteroids must be designed for increased impact risk. Comet missions face even greater challenges. Comets are surrounded by clouds of dust shed from their icy cores. This dust travels with the comet, but not uniformly. It forms streams and pockets of higher density. The ESA's Rosetta mission to Comet 67P, Churyumov-Gerasimenko, operated in this dusty environment for 2 years, carefully navigating through regions of varying particle density to minimize impact risk. Interstellar space presents unknown micrometeoroid risks. The 2 Voyager spacecraft and New Horizons have exited or are exiting the solar system, entering the interstellar medium. Micrometeoroid densities there are uncertain. The spacecraft may encounter more or fewer particles than in the solar system. We'll learn as these spacecraft continue reporting. Micrometeoroids are a constant, unavoidable hazard. Unlike space debris, which is concentrated near Earth and could theoretically be cleaned up, micrometeoroids are natural and pervasive throughout the solar system. Shielding provides protection against small particles, but larger impacts remain a threat. Every spacecraft, every mission, carries this risk: tiny bullets traveling through space, mostly harmless, occasionally deadly. Space has no temperature vacuum, can't be hot or cold. But objects in space experience extreme thermal conditions depending on sunlight exposure. In direct sunlight, surfaces can reach over 250 degrees Fahrenheit, 120 degrees Celsius. In shadow, temperatures plummet to below -250 degrees Fahrenheit, -150 degrees Celsius. Managing these extremes is critical for spacecraft and astronaut survival. The thermal challenge stems from how heat transfers in space. On Earth, heat moves via conduction through materials, convection through fluids like air or water, and radiation, electromagnetic waves. In space, there's no atmosphere, so convection doesn't exist. Conduction occurs through materials, but without air, heat can't transfer between separated objects. Radiation is the primary heat transfer method. Objects absorb sunlight and radiate infrared energy. The Sun delivers about 1,361 watts per square meter at Earth's distance, the solar constant. A spacecraft in sunlight absorbs this energy, heating up. How much it heats depends on its absorption and emission properties. A black surface absorbs sunlight efficiently and heats more than a reflective surface. But black surfaces also radiate heat efficiently. White surfaces reflect sunlight but radiate less effectively. Thermal design involves balancing these properties. The ISS experiences temperature extremes as it orbits. In sunlight, external surfaces facing the Sun can exceed 250 degrees Fahrenheit. In shadow during orbital night, which lasts about 45 minutes per orbit, those same surfaces cool rapidly to below -150 degrees Fahrenheit. This thermal cycling stresses materials, causing expansion and contraction. Over years, this can fatigue materials and cause failures. Inside, the ISS maintains comfortable temperatures around 70 degrees Fahrenheit, 21 degrees Celsius. This requires active thermal control. The station has radiators, large panels that emit infrared radiation, cooling the station. Fluid loops circulate coolant through the station, collecting heat from equipment and crew, then pumping it to radiators where it's radiated into space. Managing heat inside spacecraft is challenging. Humans generate heat about 100 watts per person. Electronics generate heat, computers, life support, lighting. In the closed environment of a spacecraft, this heat accumulates. Without active cooling, temperatures would rise dangerously. The ISS's cooling system has redundant loops. If one fails, backup systems can maintain temperatures, though with reduced capacity. Occasionally, cooling loops have had problems, leaks, pump failures, forcing temporary heat management measures like turning off non-essential equipment or adjusting crew activity levels to reduce heat generation. Spacesuits face unique thermal challenges. The suit must keep an astronaut comfortable in extreme conditions, exposed to direct sunlight on one side and deep cold on the other. Modern spacesuits use liquid cooling garments, tight-fitting undergarments with tubes circulating cold water. The water absorbs heat from the astronaut's body and carries it to the suit's backpack, where it's cooled by radiators or sublimators, devices that evaporate water into space, carrying away heat. During spacewalks, thermal management is critical. An astronaut working hard generates substantial heat, more than the suit's cooling system can remove. If cooling fails, the astronaut overheats rapidly, a dangerous situation. Conversely, an astronaut resting in shadow might become too cold. Suit systems constantly adjust cooling levels based on the astronaut's activity and environmental conditions. The Moon presents extreme thermal challenges. Without atmosphere to moderate temperature, the lunar surface in sunlight reaches about 250 degrees Fahrenheit, 120 degrees Celsius, while in shadow it drops to about -290 degrees Fahrenheit, -180 degrees Celsius. Lunar nights last about 2 weeks, during which surface temperature plummets. Apollo astronauts landed during lunar morning when temperatures were more moderate and left before peak heating or cooling. Future lunar bases will need robust thermal management. Habitats must be insulated against temperature extremes. Power systems must operate in both hot and cold conditions. Equipment left on the surface will cycle through extremes every lunar day, night, causing thermal stress. Mars has less extreme temperature swings than the Moon because it has atmosphere thin but sufficient for some convective heat transfer. Daytime temperatures near the equator can reach 70 degrees Fahrenheit, 20 degrees Celsius, while nighttime temperatures drop to -100 degrees Fahrenheit, -73 degrees Celsius. At the poles, temperatures reach -195 degrees Fahrenheit, -125 degrees Celsius during winter. Human missions will need heating and cooling systems, though less extreme than required on the Moon. Spacecraft visiting other planets face even more extreme conditions. Mercury, closest to the Sun, has daytime surface temperatures around 800 degrees Fahrenheit, 430 degrees Celsius, and nighttime temperatures around -290 degrees Fahrenheit, -180 degrees Celsius, the most extreme temperature range in the solar system. The outer solar system is perpetually cold. Jupiter's orbit receives only 4% of the sunlight Earth gets, and beyond, it's colder still. Thermal design for these environments is complex. Spacecraft use multi-layer insulation reflective blankets preventing heat loss or gain. Active heating uses radioactive isotope thermoelectric generators or electric heaters powered by solar panels. Cooling uses radiators, heat pipes, or phase change materials. The Cassini spacecraft orbiting Saturn used RTGs for heat and power. At Saturn's distance, sunlight is too weak for solar panels. The RTGs produced heat as a byproduct of radioactive decay, keeping instruments warm in Saturn's cold environment, about -285 degrees Fahrenheit, -176 degrees Celsius, in orbit. The Parker Solar Probe, launched in 2018, approaches the Sun closer than any previous spacecraft, within 4 million miles of the surface. At this distance, sunlight intensity is about 500 times greater than at Earth. The probe uses a thick heat shield to protect instruments, keeping them at room temperature, while the shield itself heats to over 2,500 degrees Fahrenheit, 1,370 degrees Celsius. Thermal extremes affect material properties. Metals become brittle at very low temperatures, more prone to cracking. Plastics and rubber lose flexibility. Lubricants freeze. At high temperatures, materials weaken, expand, and can deform. Electronics have operational temperature ranges too hot or too cold, and they fail. Batteries are particularly temperature sensitive. Cold reduces capacity. Heat accelerates degradation. Spacecraft batteries often have heaters to keep them warm and cooling systems to prevent overheating. Rovers on Mars have struggled with cold soak during nights. requiring heaters to keep batteries and electronics functional. The Spirit and Opportunity rovers on Mars carried RTG-powered heaters to survive frigid nights. Even so, cold affected their performance. The InSight lander's seismometer was so sensitive that thermal creaking noises from the lander's structure expanding and contracting with temperature had to be filtered out from seismic data. Thermal management isn't just engineering, it's survival. Without proper control, astronauts overheat or freeze. Equipment fails, missions end. The thermal extremes of space are constant, unforgiving, and inescapable. Managing them is one of the great challenges of space exploration. Space is vast, empty, and isolating. Astronauts on missions face psychological challenges unlike anything on Earth. Confinement in small spaces, separation from family, danger, and the profound isolation of being farther from help than any human in history. These psychological stresses are real, serious, and potentially mission-threatening. On the ISS, astronauts live in a module about the size of a 6-bedroom house, shared with 5 or 6 other people. They can't go outside except for carefully planned, highly constrained spacewalks. They can't leave. They're stuck together for 6 months, seeing the same people, the same walls, every day. Most astronauts handle this well. They're carefully selected and trained. Psychological screening eliminates candidates who can't handle confinement or isolation. But even the best prepared astronauts experience stress. Personality conflicts arise. Frustrations build. Tempers flare. NASA and other agencies work hard to prevent and manage these issues, but they're inevitable to some degree. Historical examples show the risks. During the Skylab missions in the 1970s, crews reported feeling overwhelmed by the constant workload, leading to a one-day unscheduled break where astronauts turned off communications and took time for themselves, a strike in space, though NASA officially termed it a work schedule adjustment. The incident highlighted that even highly motivated astronauts need downtime and autonomy. On the Russian Mir space station, longer missions and more cramped conditions led to notable incidents. Personality conflicts between crew members sometimes strained mission operations. In one well-documented case, an American astronaut and a Russian cosmonaut had a contentious relationship, causing tension that affected the entire crew. Ground controllers had to mediate conflicts and adjust work schedules to minimize friction. Isolation's effects intensify on longer, more distant missions. Mars missions 2 to 3 years total, including travel and surface time, will test human psychology to unprecedented levels. Astronauts will spend months in a spacecraft smaller than the ISS, unable to return if problems develop. Communication delays up to 22 minutes round trip at Mars's greatest distance mean real-time conversations with Earth are impossible. Astronauts will be truly alone in a way ISS crews never are. The third quarter phenomenon, a psychological slump occurring around the three-quarter point of a long mission, is well documented in polar expeditions, submarine patrols, and space missions. Morale drops, Conflicts increase, and performance can decline as the end seems frustratingly distant, yet the novelty has worn off. Mars missions will need strategies to counter this effect. Confinement compounds stress, small spaces, lack of privacy, and constant proximity to the same people wear on psychological well-being. Submarine crews experience similar challenges. Studies of long-duration submarine patrols show that crew members develop coping strategies in formal schedules for using shared spaces, respect for personal time, and understanding that minor irritations must be tolerated. Sleep disruption is another factor. On the ISS, sunrise occurs every 90 minutes, 16 sunrises per day. This disrupts circadian rhythms. Astronauts use sleep schedules, blackout shades, and sometimes medication to maintain regular sleep. But irregular sleep degrades mood, cognition, and health. Long-term poor sleep can cause serious psychological problems. Sensory deprivation contributes to stress. Space is silent, no wind, no rain, no ambient noise except equipment hum. The environment is visually monotonous, grey walls, similar modules, little color. Astronauts bring personal items, music, photos to add variety, but the environment remains austere, contributing to psychological strain. Danger creates constant background stress. Astronauts know they're in a hostile environment, dependent on machines for survival. Any failure, loss of pressure, fire, toxic atmosphere could be fatal. This knowledge creates low-level chronic stress, affecting sleep, mood, and cognition. The overview effect seeing Earth from space provides psychological benefits. Many astronauts describe profound emotional experiences seeing Earth a beautiful, fragile sphere in the blackness. This perspective can be inspiring and uplifting, but it also brings awareness of distance and isolation. Home is visible but unreachable, emphasizing how far away and alone they are. Cultural differences can cause friction. International crews on the ISS come from different countries with different communication styles, work habits, and expectations. While astronauts are trained to work internationally, cultural misunderstandings occasionally occur. Language barriers, missions operate in English and Russian, can complicate communication during stressful situations. Family separation is difficult. Astronauts miss important events, birthdays, anniversaries, births. Communication with family is possible but limited email, video calls, and subject to delays and bandwidth limitations. Knowing family is struggling or needing support while being unable to help creates emotional pain. NASA and other agencies provide psychological support. Crew members can speak confidentially with psychologists. They're encouraged to maintain Earth routines, meals together, leisure time, exercise. Supplies include comfort items, favorite foods, personal entertainment. Video calls with family are prioritized, but these are imperfect solutions. Antarctica research stations provide analogous experiences. Winter over crews at isolated stations like McMurdo or Amundsen Scott spend months in confinement, cut off from resupply or evacuation in extreme environment. Studies of these crews inform space mission planning. Lessons include the importance of autonomy, the value of hobbies and personal projects, and the need for structured but flexible schedules. Mars missions will require even more psychological resilience. Crews will need exceptional compatibility, robust conflict resolution skills, and mental toughness. Mission planners are developing crew support strategies, habitat designs with private spaces, entertainment options, communication protocols with Earth, and activities to maintain morale. Some propose sending small crews 4 to 6 people to reduce interpersonal complexity. Others suggest larger crews to increase social diversity. Both approaches have merits and drawbacks. Crew composition mix of personalities, skills, and backgrounds will be critical. Selection will emphasize psychological compatibility as much as technical skills. Virtual reality could help. Simulated environments, walking through forests, visiting cities, seeing family, might provide psychological relief from confinement. Early experiments on the ISS with VR headsets show promise. Astronauts report enjoying the immersion and novelty. Art, music, and creative activities help. Astronauts paint, play instruments, write. These activities provide mental stimulation and emotional expression. Future long-duration missions might include dedicated creative spaces, art studios, music rooms to support crew well-being. Despite challenges, humans are remarkably adaptable. Astronauts routinely complete 6-month missions successfully. Submariners patrol for months. Antarctic crews winter over in isolation. We can handle it with proper selection, training, support, and mission design. But the psychological challenges of space shouldn't be underestimated. Mental health is as critical as physical health. A psychologically impaired crew is a mission risk. As we venture farther to Mars and beyond, understanding and supporting human psychology in space will be as important as rockets, life support, or radiation shielding. The human factor may be the ultimate challenge of deep space exploration. We've journeyed through space's real dangers: vacuum, dust, debris, static, inertia, radiation, micrometeoroids, thermal extremes, and psychological strain. Each is serious. Each has killed or could kill. Together, they make spaceflight one of humanity's most dangerous endeavors. Yet, we continue exploring. Despite the risks, astronauts volunteer. Despite the costs, nations invest. Despite the dangers, we keep reaching farther back to the moon, onto Mars, and eventually beyond. Why? Because the dangers, while real, are manageable. Engineering, training, and careful planning mitigate risks. Every mission teaches lessons. Every failure drives improvements. We learn from accidents like Apollo 1, Challenger, Columbia tragedies that refined our understanding and made spaceflight safer. The dangers are part of exploration's nature. Early maritime explorers faced storms, scurvy, unknown waters. Aviation pioneers faced crashes and mechanical failures. These dangers were overcome through knowledge, technology, and determination. Space is no different, just a new frontier with new challenges. Understanding space's dangers is essential. Ignorance invites disaster. Knowledge enables preparation. Every astronaut knows the risks. They train for emergencies, wear protective equipment, follow procedures designed to keep them safe. They accept the dangers because they believe exploration is worth it. The hazards of space push technology forward. Developing radiation shielding advances materials science. Managing thermal extremes improves insulation and cooling. Mitigating debris drives tracking and mitigation technologies. Space's challenges inspire innovations that benefit Earth medical imaging, water purification, materials science, and more. Space's dangers also remind us of our fragility. We're adapted for Earth, its atmosphere, gravity, temperature, radiation shielding. Leaving Earth means entering an environment where we don't belong, where survival requires constant vigilance and technological support. This humbles us, providing perspective on our place in the universe. But the dangers don't stop us. The International Space Station has been continuously inhabited for over 2 decades. Hundreds of astronauts have lived there safely. Spacewalks are routine. Supply missions arrive regularly. We've made low Earth orbit accessible and relatively safe, not without risk, but manageable. Looking forward, we'll venture beyond Earth orbit. Artemis missions will return humans to the Moon. Eventually, humans will walk on Mars. These missions will face greater dangers, longer exposure to radiation, isolation, and all the hazards we've discussed. But we'll manage them, learning and adapting as we go. New technologies will help. Better radiation shielding, advanced life support, autonomous systems, improved materials, all will make space safer. We'll never eliminate risk entirely, but we can reduce it to acceptable levels. The psychological challenges may be hardest. Technology can shield against radiation and debris, but isolation and confinement require human resilience. Selecting and supporting crews for Mars missions will require unprecedented understanding of psychology. But humans are resourceful. We adapt, we endure, we overcome. As you drift towards sleep, reflect on the astronauts who face these dangers. They float above you now on the ISS, orbiting every 90 minutes, enduring vacuum, radiation, debris, and all the hazards of space. They do it willingly, accepting risks most of us would find terrifying, because they're driven by curiosity and the desire to explore. They're modern pioneers, venturing into a hostile frontier, expanding human presence beyond our home world. The dangers they face are real, but so is their courage. They represent our species' restless drive to explore, to understand, to reach beyond our limits. Tomorrow, they'll continue their work, conducting experiments, maintaining equipment, preparing for future missions. The dangers remain, but so does the mission. Space is dangerous, but it's also magnificent, full of wonders we're only beginning to understand. Rest well, knowing that despite the dangers, humans are reaching for the stars. The hazards are many, but our determination is stronger. We'll face the dangers, manage the risks, and continue exploring, because that's what humans do. We dream, we dare, and we venture into the unknown, accepting danger as the price of discovery. Sweet dreams, fellow traveler. The cosmos awaits, dangerous yet irresistible, and we'll meet its challenges, one mission at a time, pushing farther, learning more, and eventually making even the dangerous void of space feel a little more like home.